Unfortunately, the following two presenters got some technical problems, but luckily the next presentation was to be given by Ilyashenko from Moscow State University of Civil Engineering, but her colleague Sergei Kuznetsov can partly present her research and combine that with his presentation. So now I give podium to Sergei Kuznetsov, and he will present both the report of Ilyashenko that is entitled "On Non-Existence of the Interfacial Stoneley Waves," and his own presentation that is entitled "Stoneley Circular Equation at Wiechert Condition." So, Professor Kuznetsov, please use.
Volodya, thank you very much. Unfortunately, I have no enough material to just spread over two presentations. So my presentation will be about 20 minutes, not more. But I'll try to incorporate all the materials from both. So the presentation will combine both. I'll speak on Stoneley circular equation and Wiechert condition. Actually, Stoneley waves are derived, the basic equations for Stoneley waves were derived by Robert Stoneley. It was in 1924. He described that wave as a wave that propagates along the interface, plane interface between two half spaces. Here, this situation is shown. So that is a plane interface between two dissimilar half spaces. That is direction of propagation of that Stoneley wave. And what was found? That Stoneley waves attenuate with depths in both of the half spaces. Attenuation is exponential. And in that case, these waves resemble what is known for Rayleigh waves. They also attenuate with depth exponentially. Then, again, there is direct similarity. Speed of propagation of these waves is not dependent upon frequency. The same is for Rayleigh waves. That is called non-dispersive velocity or non-dispersive speed of propagation. But the speed of propagation depends upon physical properties of the contacting half spaces. And in that respect, the situation is different comparing to Rayleigh waves, because Rayleigh waves exist for any kind of material parameters of the medium. However, for Stoneley waves, the dependence is much more strict. Means shear bulk wave velocity of the half spaces, minimal one, and here CR means speed of propagation of Rayleigh wave, again minimal one, corresponding to these half spaces. What else known for Stoneley waves? They arise at earthquakes. It's known when bulk waves emanate from the focus of the earthquake. Then at the interfaces between the layers, Stoneley waves begin to propagate, and much of the energy associated with earthquakes is carried out by Stoneley waves. In technical geophysics, these waves are used for seismic analysis, for analysis of the soil formations when borehole is drilled, and then along the vertical line of the borehole, a kind of waves that very similar to Stoneley waves can propagate. Actually, the situation is more complicated because here in the so-called outer Pogamer-Cree waves are emanating, but geophysicists very often use a more simple model for Stoneley waves. The Stoneley waves can arise even at analyzing layered plates. Here we see multi-layered plates where LAM waves propagate. Here is a sample of dispersion curves. On horizontal axis is speed of propagation, phase speed, and vertical axis denotes frequency of propagation. So we have different waves at very high frequencies. Situation is shown here, and you see that there are three peaks. The first one relates to propagation of a Rayleigh wave. The third one concerns with propagation of shear bulk wave, and here several peaks uniting in one are associated with appearing Stoneley waves. And such situation, appearing of Stoneley waves, is characteristic not only for layered media of finite of natural thickness, but even for micro and nano layers. For analyzing Stoneley waves, we need to analyze waves of very high frequencies. Now, some mathematical preliminaries for Stoneley waves. The first two equations at K1, K2 are ordinary dynamic equations used for isotropic media. A and B are correspondingly longitudinal and shear bulk wave velocities. U is the displacement field, and index K denotes one or second half spaces. That equations of motions should be accomplished by the interface continuity conditions. These are concerned with displacement fields, and d omega denotes boundary surface, interface surface, and t nu are surface traction fields acting on that p nu plane. So displacement should be continuous, and stresses acting on the on the interface surface should also be continuous. These two conditions, equations of motions and interface continuity conditions, should be accomplished by the Sommerfeld attenuation condition, which means that both displacement and stress should vanish at infinity. When infinity, I mean at depths of both the half spaces. Now, how to get the equation, secular equation that is needed for obtaining Stoneley wave velocity. The exponential representation for the displacement fields in both of the half spaces should be taken into account. That exponential multiplier is for harmonic wave motion along the interface. Here it is. We assume that along the interface, the wave is harmonic in both that coordinate and time. And in that directions, the wave should attenuate. And that attenuation is given by that term. We assume that amplitude of displacements in both of the half spaces should be exponentially decaying. After substituting that representation, Stoneley derived his secular equation. What can be seen? Here is c, that is speed of propagation of Stoneley wave in the fourth order. Here is in the second order, and we almost lucky saying that it is almost a polynomial equation. However, it's not our case, because speed of propagation also is here under square roots, and unfortunately this equation, being algebraic, is not reducible to the polynomial one. And that is the most important thing that up to now prevented from obtaining numerical solutions for speed of approximation, speed of propagation. What is only known that for some kinds of very specific kinds of elastic isotropy, Stoneley waves can exist. With that equation derived by Stoneley, it is not very easy to work. So Scholter later on suggested another form of this equation, transforming to dimensionless variables, dimensionless speed, dimensionless density as a ratio of two densities, dimensional bulk wave velocity. Again, a ratio of bulk waves, and here B2, beta 2 is speed of propagation in second half space. I could use first half space or even combination of two half spaces, but due to Scholter, he chose that kind of combination of parameters. So in most general case of two isotropic half spaces are in contact, our problem is reduced to 4 undimensional parameters: densities, shear, relative shear, bulk wave velocity, and 2 relative longitudinal bulk velocities. Even with dimensionless parameters, obtain any kind of solution wasn't possible until now. What is known? There are some numerical examples obtained by Stoneley, Scholter, Sizawa, Kanyar, Murty, and several other researchers. Up to now, there are a lot of works on obtaining regions of existence for Stoneley waves. And that is a typical region of existence obtained by Sizawa and Kanai. Here is, he assumed that both contacting media have the same Poisson's ratio. They fixed Poisson's ratio. Actually, that picture is for Poisson's media when Poisson's ratio is 0.25. So our problem is reduced fixing Poisson's ratio. Our problem reduces to the two-parametric problem with relative densities and relative Lames constants. Here he varied on horizontal axis relative density. Along vertical axis he varied relative Lame's constant and obtained that within that two curves, Stoneley wave can exist. Out of these curves, regions of non-existence. Later on, these curves were reproduced almost in the same manner, but for different Poisson's ratios. However, recently, Ilyasov and Ilyashenko made numerical computations, obtained that regions of existence. You see here, this region resembles what was found by Sizawa and Kanai. However, they have found that that point in the center with coordinate 1 and 1 is absent from the region of existence. And here, that point was denoted by A. What does this point mean? Look here at relative density equal to unity. That means that both densities are equal. At relative mu equal to unity means that both Lame's constant are equal. So acoustically, that media becomes a homogeneous one. In homogeneous medium, when there is no separate boundary, no surface acoustic waves can propagate. And that justifies their finding that that point should be excluded from consideration. But the question is open, whether along with that particular point, some vicinity of the point maybe should also be excluded. And that is an interesting thing that was observed only recently. And now we proceed to the Wiechert condition. It was found by Emil Wiechert in the beginning of the 19th century, of 20th century. Wiechert considered the following case: when relative Lame constant lambda, relative Lame constant mu, and relative density have the same values equal to some parameter. Here it is denoted as q, and it is called the Wiechert parameter. He assumed that upper layers of the Earth's crust obey that relation, and since his discovery, a lot of geophysical researchers incorporate that assumption that these parameters are equal, and that equation is known as Wiechert equation or Wiechert condition. At Wiechert condition, we can easily found, dividing by rho, that in both half spaces longitudinal waves should be equal. It concerns with longitudinal bulk wave and shear bulk wave velocity. And hence, immediately follows the following result. At Wiechert condition, both Rayleigh wave velocities in the half spaces should be equal. However, Stoneley wave can exist because even if these parameters are equal, still there is a chance for Rayleigh wave to be existent. That kind of condition, Wiechert condition, can be explained as a straight line in the 3D space generated by the dimensionless parameters lambda, mu, and rho. And that line, because they are equal, has equal guide cosines to the axis of that space. That line is known as the Wiechert line. And along the Wiechert line, taking into account Wiechert condition, the Stoneley wave equation can be given in, can be written in such a way with modified coefficients. Here, these coefficients are given, and note that along Wiechert line, both half spaces have the same bulk wave velocities that are denoted here without indices. And suppose that dimensionless density equals to unity. Then that coefficient disappears, this disappears, and our equation that also disappears. Our equation becomes as follows, very simple equation. Unfortunately, that equation has no roots except trivial. C is vanishing. And that is clearly demonstrated on that slide, on that figure. If relative density is equal to unity, then we are in the region of non-existence. So no Rayleigh wave can exist. And now my my recent analysis done for variation of Stoneley wave velocity along Wiechert line. That was done numerically by numerical computations for different Poisson's ratios, both half spaces along Wiechert line. Both half spaces have equal Poisson's ratio. Here it was varied from 0 to 0.4. We observe here that all these lines correspond to decaying velocity with increasing Wiechert ratio, Q, at very large values of that Q, it appeared that these tend to the Rayleigh wave velocity in the half spaces, and at very small values of Q approaching to unity, these velocities approach to velocity of bulk waves in the contacting half spaces. And that is presumably the velocities along the Wiechert line. And now some problems that I tried to solve but failed. Conditions of Stoneley wave existence for isotropic contacting media that do not obey any restrictions like Wiechert condition. The same concerning anisotropic media. That is like terra incognita. Then, of course, it's very interesting to obtain analytical expressions for Stoneley wave velocities for isotropic media, and of course, if possible, for anisotropic media. As far as I know, nothing in that respect is obtained up to now. Then resolving the problem of existence in the vicinity of the point 1,1, that point A, on the Wiechert line. Whether only one point should be excluded or some vicinity of that point. Apparently, nothing is done in that respect as well. Then leaky Stoneley waves propagating with velocities exceeding minimum shear bulk wave velocity in the half spaces. Again, this problem is interesting for analyzing, as leaky waves play an important role in applied geophysical applications of analyzing layer structure of the upper layers of the Earth's crust in applied geophysical application. And then polarization of Stoneley waves. Maybe you remember that Rayleigh waves have elliptical polarization, and it is well known. Polarization was obtained by Lord Rayleigh. It was in 1885. However, for Stoneley waves, apparently nothing is done concerning polarization of that waves. Then stress fields associated with propagation of Stoneley waves. Also, nothing is known. Energy variation and energy flux associated with Stoneley waves. New works done with this respect. And what was considered by Danilo Prikashikov in his recent report, when he analyzed modification of boundary conditions when some thin layer is placed above the half space, the same problem is actual for Stoneley waves that can propagate on the interface with non-classical boundary conditions that may account, say, slippage mechanism or some soft thin layer between two half spaces and so on. And that is actually the last slide, but one. Here are some publications on Stoneley wave analysis, starting from Stoneley pioneering work to some recent publications. And thank you for your attention. The presentation is available at the following address. Thank you very much.
Thank you for your presentation. Can I ask you the first question? So it's how do you think what kind of experiment can be done in order to observe these Stoneley waves and maybe check the applicability of your solutions, and maybe also help answering the questions that you raised on your last slide? Will that be easy or?
Well, concerning experimental verification, there are some interesting works on propagation in terahertz region waves in layered structures. However, it's difficult to compare because only sporadic points were found, not the whole dispersion curve. Well, it's possible to compare, but we didn't make such comparison yet.
Also, the experiment is very difficult.
Yes, I suppose the experiment is heavy to produce, difficult to produce.
Yeah, thank you very much. Questions, please. The paper is open for discussion. Okay, so if there are no questions, I can check also the raised hands. Yeah, thank you very much once again.